So we have particle and continuum practice final exam, first year doctoral level in physics. So let's begin with number one. A particle of mass m moves in one dimension with action, and this action functional s of x. That equals this integral from t sub 1 to t sub 2, bracket 1/2 m x dot squared minus lambda over 4 x to the fourth plus alpha x squared x dot close bracket dt. So for part A, we want to derive the Euler-Lagrange equation. Part B, explain whether the term alpha x squared x dot changes the equation of motion. And part C, determine the conserved energy. So this is a least action principle problem. So the action here, S of x, equals this t sub 1 to t sub 2. Given here, bracket 1/2 m x dot squared minus lambda over 4x to the fourth plus lambda x squared x dot, close bracket dt. So the Lagrangian here is going to be L equals 1/2 m x dot squared minus lambda over 4x to the fourth plus alpha x squared x dot. And moving on here, the Euler-Lagrange equation, this partial derivative L with respect to x dot, that equals m x dot plus alpha x squared. So ddt, partial derivative L with respect to x dot equals m x double dot plus 2 alpha x x dot. So our partial derivative L with respect to x is negative lambda x cubed plus 2 alpha x x dot. So our Euler-Lagrange equation is here d dt, partial derivative of L with respect to x dot, minus the partial derivative of L with respect to x, set equal to 0. So from here, what we could do is we could substitute in m x double dot plus 2 alpha x x dot minus the quantity negative lambda x cubed plus 2 alpha x x dot equals 0. The alpha terms are going to cancel, and mx double dot plus lambda x cubed, that equals 0. So the equation of motion is going to be mx double dot equals negative lambda x cubed. And building on that, part B, explain whether the term lambda x squared x dot changes the equation of motion. Moving to part B here. So we have, does alpha x squared x dot change the motion? So we could say no. The term term alpha x squared x dot is a total time derivative because alpha x squared x dot equals d dt alpha over 3 x cubed. So it changes the action only by a boundary term. So the integral from t sub 1 to t sub 2, alpha x squared x dot dt, when we compute this, it's going to be alpha over 3 x cubed from t sub 1 to t sub 2. And for the fixed endpoints, and pardon me for that poorly drawn delta x of t sub 1, that equals delta x of t sub 2 equals 0. So, and this boundary term does not affect the variational principle. So alpha x squared x dot does not change the equation of motion. Okay. And pardon me if I mispronounced anything. I'm a little uncaffeinated today. I didn't have enough caffeine. Part C, conserved energy. Since L has no explicit time dependence, the conserved energy is going to be E equals x dot, partial derivative of L with respect to x dot minus L. Prior to this, we already found that the partial derivative of L with respect to x dot is mx dot plus alpha x squared. So E equals x dot times the quantity mx dot plus alpha x squared minus this quantity 1/2 mx dot squared minus lambda over 4x to the fourth plus alpha x squared x dot. So going ahead and expanding this, E is going to equal mx dot squared plus alpha x squared x dot minus 1/2 mx dot squared plus lambda over 4x to the fourth minus alpha x squared x dot. And what happens here, the alpha terms, they're going to cancel, and E is going to equal 1/2 mx dot squared plus lambda over 4x to the fourth. So we get that E equals 1/2 mx dot squared plus lambda over 4x to the fourth. Okay, so that is problem number 1. Thank you very much and have a great day.